number 7 through 14 say to use the figure at the right to find the measure of the arc or angle. Explain your reasoning. They do tell us that ABCDEF is a regular hexagon, okay? So let's go ahead before we start. I usually do this, students. You're used to me going through first and just writing numbers in instead of looking for certain answers for questions that they ask us. So I'm going to go ahead and first of all highlight the hexagon. Here's the hexagon. Now you guys understand if it's a regular hexagon, that means all of the angles here are going to be congruent on the inside, okay? So understand that, but also we can make another very true assumption without any doubt that all of these arc lengths right here, well, it's not an assumption, sorry. Remember, if a chord is equal, then its arc is also equal. So if this chord here is congruent to this chord here, then this arc is congruent to this arc, and we can continue that pattern around the entire circle, because in a regular hexagon, all of these sides are congruent. So if this side is congruent to this side, then this arc is congruent to this arc. So right off the bat, I have a bunch of arcs that are congruent. Now how many arcs do I have on the circle? 1, 2, 3, 4, 5, 6. I have 6 arcs. Well, if I go around the entire circle from C all the way to C, I know that's going to be 360. So take 360 and divide it by 6, and all of these arcs have to be 60 degrees, okay? So I'm not going to go through and write 60 over and over, but I'll write it 3 times, okay? So that's a start. That's going to help me a lot with my angles. Also, if you have a regular hexagon, which that's a very poor drawing of a regular hexagon, but pretend that's a regular hexagon. Remember, we know what the sum of all these angles are, okay? We know you can take 180 and minus 2. So if there's 6 sides, 6 minus 2 is 4. So 180 times 4 is 720. So we know all 6 of these angles have to add up to 720. And we know all 6 of those angles are equal because it's a regular hexagon. So divide this by 6 and you get 120. So all of the angles inside of a regular hexagon are 120, okay? So that's something else I'm going to write down here that might help me later. This angle here is 120 degrees, as is this angle here, 120 degrees. Now let's go ahead and try to answer some of these, okay? What is the measure of angle COD? Well, first of all, in the directions it said we're dealing with circle O. So if we're dealing with circle O, that means O is the center. So angle COD is a central angle, not an inscribed angle, but a central angle. And central angles are always congruent to the arc they intercept. So this arc right here is 60. So this angle here has to be 60 also, okay? So the answer to number 7 is 60. All right, number 8, angle CAD. Well, let's see here, C, then A, and then D. Now, students, that's what we call an inscribed angle, because the vertex is on the circle itself, and an inscribed angle is always half as big as its intercepted arc. So here's the angle, starts here, goes to here, so the intercepted arc is 60, so half of 60 is 30, so the answer to number 8 is going to be 30, alright? Alright, so let's pull this down here, 30 degrees. Alright, number 9 is DOF, so DOF. Now, okay, think about this, guys. This arc from here to here is 60, and this arc from E to F is 60. Okay, don't forget that. Now, having said that, look at the angle we're dealing with, angle DOF. That's a central angle, correct? So that means the arc that goes from D all the way to F is going to be the same as this angle here. Central angles always equal the arc that they intercept. So if from D to E is 60 and E to F is 60, then the arc DF is 60. So this angle here also has to be 60. I'm going to go ahead and write that in there in case I use that later. You never know. So that's 60. That means this is 62 because we have vertical angles right there. Alright, so DOF is 60. Okay, where did I mess up at? Oh, my bad, 120, because DE is 60 and EF is 60. 60 plus 60 is 120. So these two angles here would be 120. And I apologize for that little mistake. So 120, 120. Alright. Moving on. Number 10, angle CFE. So CFE, here it is, C to F to E. That's called an inscribed angle. And so the arc that's intercepted for angle CFE is the arc that goes from C all the way to E. Well, that's 120 degrees. An inscribed angle is always half of its intercepted arc. So if this from C to E is 120, then half of that is 60. This angle right here has to be 60. So CFE should be, hopefully, 60 degrees. Alright? Alright, let's take a look at BCA angle. BCA. Alright? BCA. Now, let's think this through, okay? First of all, I'd like to show you that we have a triangle here, alright? Very good. Now, we know for sure that this side here is congruent to this side here because they're sides of the hexagon, and it's a regular hexagon, and all the sides are congruent. So I can put a tick mark here, or a little slash here, and a slash here. Now remember, in a triangle, if two sides are congruent, then their opposite angles are congruent. So this angle here has to be congruent to this angle here. So if this is 120, the only thing left is 60. So it has to be 30 here and 30 here, because 30 plus 30 is 60, plus 120 is 180. And we all know the three angles inside of a triangle have to add up to 180. So this angle right here is 30. Don't forget that, okay? So I'm going to get rid of all this mess here. So we're trying to find the measure of angle BCA. BCA. Well, that's 30 degrees like I just showed you. So the answer is 30 degrees. Alright, arc AC. AC, well, arc A all the way to C is two arcs of 60. AB is 60. BC is 60. So the entire arc is going to be 120 degrees. Arc CBF. So C to B to F. That's a semicircle, guys. CBF. That's a semicircle. How do I know that? This is the diameter. It's a chord that goes through the center of the circle. So a semicircle always has an arc measurement of half a circle, which is 180. So arc CBF is 180. Arc CAD, so go from C to A to D. So it's the whole circle except 60. So take 360 minus 60, and you will get 300, which is the answer. Alright, moving on to numbers 15 through 18. The directions say to find the measure of angles A and B, and then find arc C. Well, first of all, arc C is pretty simple. In all of these problems, numbers 15 through 18, they're all dealing with circle O. So if this is circle O, then this has to be a diameter. If that has to be a diameter, then this has to be a semicircle. Now, semicircles are always 180. So if from here to here is 50, then arc C from here to here must be 130 to give you a total of 180. So arc C is going to be 130 degrees. Arc C equals 130 degrees. Now, angle A is a central angle because the vertex is at the center and its intercepted arc is 50. So angle A is going to be 50 degrees. And then angle B is an inscribed angle. See this? That's an inscribed angle. Forget this segment here. We don't even need that segment. Just pretend it's not there. This is an inscribed angle, okay? And it intercepts this arc here. Inscribed angles are always half of its intercepted arc. So angle B is going to be half of 50, which is 25 degrees, all right? Let me check the answers and make sure that's right. And yes, that is correct. All right, now, let's take a look at, first of all, let's take a look at arc C. First of all, arc C equals 50 degrees, okay? And here's why. This is a diameter once again, okay? So a diameter runs from here. This is a diameter, so a semicircle runs from here all the way to here, which is 180. So let me change colors here. So from here all the way to here is 130. They tell us that. So from here to here, it has to be 50 to give you a total of 180. Okay, so arc C is 50 degrees. Now, notice angle B is an inscribed angle. Do you see and this inscribed angle intercepts the arc from here to here. Well, an inscribed angle is always half of its intercepted arc, so half of 130 is 65. So angle B has to be 65 degrees. Now, remember something, students. Whenever you have parallel lines cut by a transversal, which is what we have here, alternate interior angles are congruent. And that's what you have. A and B are alternate interior angles. So angle A must also be 65 degrees. Two parallel lines cut by a transversal, alternate interior angles are congruent. Let me check the answers. Yes, that is correct. Moving on. Okay, now we're going to have to do a little work off to the side here. So let me trace this triangle here for you guys, because I'm such a nice teacher. And then we're going to trace this triangle here to help you guys see this a little bit, okay? Now let's pull this out of the way. Let's pull one triangle here, and we'll pull one triangle here, alright? Now, let's see what we can do here. First of all, do you see how this arc here is 60? You see that? Now if that's 60, look at its inscribed angle. See this inscribed angle right here? Vertex is on the circle. That means this angle here is half of 60, which is 30. That would be this angle here. So this angle here is 30. Actually, I don't even want to go there. So please accept my apologies for wasting your time. I just thought of a better way, I think a better way to do this. We learned, we have a theorem that says whenever an inscribed angle intercepts a semicircle, it is 90 degrees. So see this inscribed angle right here. Angle A is an inscribed angle. Do you see that? And notice it's intercepting a diameter, or in other words, a semicircle from here to here. So we know for sure that angle A is 90 degrees. So there's one answer right there. So put a right angle right here. But B's doing the same thing. Look, here's angle B. Angle B goes from here to here, and it intercepts this diameter right here, or this semicircle. So angle B is also going to be 90 degrees. So angle B is 90. Now why is that a big deal? That's why it's a big deal is, watch this carefully. This is 90. Now you're probably assuming that arc C is 60 because this is 60, and that's fine. That's a good assumption, and you're actually right, but I want to talk to you about why that's true. Now watch this. Do you notice how these two angles, I was going to show you how these triangles are congruent, but it just dawned on me. There's no need to do that. So, we learned a long time ago that if a chord is congruent to a chord in the same circle, then their intercepted arcs are congruent. So notice this chord here has a slash, and this chord here has a slash. That means this chord here is congruent to this chord here, which means this arc here has to be congruent to this arc here. So arc C equals 60 for that reason. I was going to try to prove congruent triangles and then go from there, but this is much easier this way. Alright, number 18. Number 18, well, first of all, we have the same situation here for number 18. See how this chord right here has a mark through it, a slash. See how this chord here has a mark through it? They're congruent. So if two chords are congruent, then their intercepted arcs are also congruent. So I know for sure that arc C is 65 degrees. That's for sure. Alright, now let's take a look at these angles. Remember, if a quadrilateral is inscribed in a circle, then opposite angles have to be supplementary. Before we get to that though, let's notice this too. We have parallel lines. See this? Look at that. Cut by a transversal. Got it? So what have we learned about consecutive interior angles? They're not congruent. They're supplementary. Got it? They're supplementary. So if this angle here is 95 degrees, then this angle here would have to be 85 degrees. Alright? So angle A is 85 degrees. Let me go over that again. You got two parallel lines being cut by a transversal. Consecutive interior angles are supplementary. So if this is 95, this has to be 85 so that they add up to 180. Now, we have a theorem that says whenever a quadrilateral is inscribed inside of a circle, the opposite angles are supplementary. So if this is 85 here, then this has to be 95 because these two angles have to be supplementary. Anytime a quadrilateral is inscribed in a circle, the opposite angles will be supplementary. Let me check the answers to make sure we're correct on this. And we are. Let's go ahead and continue on. Numbers 19 through 22. We're going to say yes. The quadrilateral can be inscribed, or a circle can be circumscribed about it, or it can't. But we have to tell why, okay? Well, first of all, we know in this problem here, a quadrilateral, all four angles have to add up to 360. So 60, 120, 280, this has to be 80. Now all four angles add up to 360. Now, are these opposite angles supplementary? Do they add up to 180? Yes. Do these two opposite angles here, do they add up to 180? Yes. So if the opposite angles are complementary, then we know for sure that the quadrilateral can be inscribed inside of a circle. So the answer is yes. Yes. Number 20. Okay, we have here a parallelogram. These two sides here are parallel, and these two sides here are parallel. So we learned that if we have a parallelogram, opposite angles are congruent. So if this is 60, this angle over here has to be what? 60. Now, let me ask you a question. Are these two angles supplementary? No, they add up to 180. Listen, students, if this quadrilateral can be inscribed in a circle, then the opposite angles have to be supplementary, and they're not. So no, this quadrilateral cannot be inscribed inside of a circle. Number 21. Now let's think this through, guys, once again. We have 60 and 120. So these two together add up to 180. Now, remember, the four angles inside of a quadrilateral, 1, 2, 3, 4, are always going to add up to 360. So if these two are 180, then that means these two here have to add up to 180 also. So we're actually going to have 90 and 90 because they're congruent. So 60 plus 90 plus 90 plus 120 is 360. Now, are these two angles supplementary? Yes. Are these two opposite angles supplementary? Yes. So can this figure be inscribed in a circle? Yes, it can be. Definitely. Alright, number 22. Number 22. Having problems with the pen here, guys, so not sure why it does this. Okay, here we go. Well, this is pretty much obvious. And this is 90 right here. This is 90 here. I mean, are the opposite angles supplementary? Not at all. 60 plus 90 is 150. 90 plus 120 is 210. The opposite angles are not supplementary. Thus, these two figures, thus this quadrilateral cannot be inscribed in a circle. Alright, moving on to numbers 23 through 30. And I'm going to pause this video real quick. This pen is really messing up here. Okay, students, so here we go. Now, my suggestion, first of all, is to do what we always do, and maybe just kind of draw some things in here. For example, well, first of all, the directions say, actually the directions don't give us much of anything. They tell us we have circle L, so we do know that L right here is the center of the circle. We do know that, okay? So, let's see what else we know. First of all, we have a quadrilateral right here. Everybody see that? And we have a quadrilateral in which the diagonals are perpendicular. Now remember what that means. This is all the stuff you've learned in the past. That's why it's so important to learn your math in the past. If you have a quadrilateral in which the diagonals are perpendicular, that means you have a rhombus. Okay, a rhombus. So, I know for sure this side here is congruent to this side here, and this side, they're all congruent. Also, we know that rhombi's diagonal, if you remember all this, if you have a rhombus, we know that the diagonals bisect bisect the angle, so I know this angle here is congruent to this angle here, and this angle here is also congruent. All four of these angles, 1, 2, 3, 4, all four of those angles are congruent. Okay, so I know that. Same thing here too, but we'll just kind of stop there. I guess we'll just go from there for now. I think that's good enough. We'll see if we have to do more later or not. Okay, arc HJ. Well, that's gonna be pretty obvious. Look, here's your inscribed angle right here. Yeah, my pen is still refusing to work properly. Here we go. Alright, so your inscribed angle goes from right there. So this inscribed angle M of 60 degrees intercepts this entire arc. Now remember, the arc's twice as big as the inscribed angle. So if this angle is 60, then the arc is going to be 120. Alright, so the answer to number 23 is going to be 120. Now 24, angle HIJ. Angle HIJ. Now let's think about this for a second here, okay? The arc from H to J, remember I just told you is 120 degrees. 120 degrees. Got it? Because the inscribed angle is 60. Now, I'm going to change colors here. If this arc is 120 here, then the arc from H all the way to J is 240 degrees. Okay? See that, okay? I'm using a mouse now, guys, so my numbers will be a little sloppy. 240. So, watch what I'm doing here, please, students. See this inscribed angle? The vertex is right here on the circle. Here goes one side of the angle right here. Again, using a mouse, so it's not very easy. Here's my vertex, okay? Now, the angle goes from there to H, alright? And then from there to J. So this inscribed angle has an intercepted arc of 240, which makes this angle right here 120 degrees. And so the answer to number 24 is going to be 120 degrees. Alright, moving on to number 27. You know what, I'm going out of order on it. That's okay. Well, let's go to 27 next. Angle HLJ. So H to L to J. Alright, now let's see if we can figure this out, okay? Angle H to L to J. Right there. Now, let's see. This shouldn't be too difficult, students. Remember, this is a central angle. HLJ is a central angle because the vertex is at the center and it intercepts this arc here. Well, central angles always equal their intercepted arc, and we already said this arc right here is 120 degrees. So if this arc from H to J is 120, then this angle here must also be 120 degrees. Alright? So 120 degrees. Now that's a big deal. By the way, I'm going to go and write something in here. It's a big deal. And I'll tell you why it's a big deal. It's a big deal because we've learned like I mentioned earlier, that a rhombi's diagonal. Here's your rhombus right here. There's your rhombus. The diagonals bisect the angles. So we just learned that this whole angle here is 120. Now if that whole angle is 120, that means this angle here with the dot is 60. I'm not going to try to squeeze 60 in there. That means this angle is 60, this angle is 60, and this angle is 60 here. So we're going to remember that those little green dots mean 60 degrees. Alright? Now, by the way, if this is 120, how do I know this is 120 right over here? Because a rhombus is also a parallelogram, and parallelograms have opposite angles congruent. Alright, number 28, ILJ, angle I to L to J. We just said it. That little green dot right there, I to L to J. That little green dot right there is 60. Okay, so we're going to go ahead and call that 60. Now, angle KIJ. So from K up to I down to J. Well, guys, that's also going to be 60. We just talked about that, okay? That's going to be 60 degrees. Number 26, segment IJ. Now, this is interesting. I want you to pay close attention, students. See this triangle right here? Everybody see that? Okay, I'm going to write that over here. So watch this carefully as I do this, alright? There it is. There's that little triangle right there. Now, I know this angle here is 90. If this angle is 90, then I know this angle here is 90 also. So, I'm going to put 90 degrees right here. I know this segment here is 6, because that's a 6. See this dot right here? I already told you guys that's 60. So if that's 60, this has to be 30. So we have a 30, 60, 90 triangle. Okay? So, if we have a 30, 60, 90 triangle, then we can use our shortcuts that we've learned. So here's 30. I probably should make this a little bigger just so we can see it. So let me do that. Take just a second to do that. Alright, now look, students. Here's 30, so this is my shorter leg. Here's 60, this is my longer leg. And this is my hypotenuse over here. Now we're trying to find the length of IJ, which is the same thing as your hypotenuse, okay? Well, if you've memorized your shortcuts for your 30, 60, 90 triangle like you're supposed to, the hypotenuse is always twice as big as the shorter leg. So if the shorter leg is 6, then the hypotenuse is going to be 12. Alright, okay, moving on to arc JM. Arc JM. Let's see here. Do we have an angle? Yes, we do. Okay, here's arc JM right here. Everybody look. Arc JM. Okay, now the angle that intercepts that arc is this inscribed angle right here. Okay, see that? This whole angle right here. So, if I can find the inscribed angle, then the arc's going to be twice as big. Well, we know this whole angle here is 30, or excuse me, 60. So we know this little angle right here has to be 30, right? 30, 60, 90 triangles. This is 60, this is 90, that angle's 30. Now, if that angle's 30, please listen to me carefully, students. Let me see if my pen will work yet. Sometimes it starts working. If this little angle here is 30, I know this little angle here has to be 30 because a rhombus is diagonals. A rhombi is diagonals bisect the angle. Now what about this angle here? Well, I would like to show you that this whole angle in blue, this whole angle here in blue, yeah, it just won't work. This whole angle here in blue is, look, it's intercepting a diagonal. I mean a diameter. Here's your diameter right here. So that means, remember, when an inscribed angle intercepts a semicircle, it's 90 degrees. So this whole angle here has to be 90 because it's intercepting a diameter. So if this is 30, if this is 30 here, and this is 30, this has to be 32, because 33, 30 is 90, this whole angle has to be 90 right here. So, if this is 30, 30, 30, then students, look at this angle right here that we're talking about, from here. Well, my pen just won't stop doing this. I wish it would straighten up. Alright, I'll just use the mouse. This angle right here is composed of this angle and this angle 30. So this angle here has to be 60. So this intercepted arc is twice as big. It has to be 120. Alright. And then finally, angle LHM. So L to H to M. Well, I just showed you that's 30. L to H to M. This is 30. So the answer is 30 degrees. Alright. Okay, moving on now to this problem here. Alright, now, explain why JB is congruent to GE and IC is congruent to HD. Sure, that's pretty simple to do, to be honest with you. I have a semicircle here, okay? Right here. Okay? And it says in the directions that all of these lines are 1 inch apart. Okay? So if they're all inch apart, then I know that JB is equidistant from the side right here. And I know GE, this line right here, is the same distance from this edge right here. Alright, so I know they have to be congruent just by the fact that it is an arc. We know these lines here are going to be vertical. In fact, it says in the directions, these are vertical segments. So I know I've got 90 degrees here, right here, 90 degrees here. So how do I know that this segment here is congruent to this segment here? I know that because they're the same distance from the edges. The same thing is true also for the next question it asks, how do I know that IC right here is congruent to HD? Well, they're 90 degrees right here. And we know they're the same distance from the edge, okay? So they have to be congruent. Now, this next question is pretty tough. I would like to know if any of you got this right. If you did, email me and let me know. This is pretty tough. How do I know this proportion is valid? Well, this is really interesting. Watch this. If I draw triangle AJF, okay, draw that triangle right there. Now, if I do that, I know for sure I have a right angle right here. Mr. Earhart, how do you know that? Well, because I have an inscribed angle. Here's my circle. And I have an inscribed angle. There's my circle. Because the angle's right here on the circle. The vertex of the angle is. And notice my inscribed angle is intercepting a diameter. See that? It's intercepting a diameter or a semicircle. So I know this angle has to be 90. Now look at this. Look at this. This is JB is an altitude. So basically what I have is this. Look guys, I have a right triangle like this with an altitude being drawn from the right angle to the hypotenuse. We've talked about this a lot, guys. This number here, we're going to call it JB. This side right, this length right here, JB, is the geometric mean of this segment and this segment. Let me say that again. JB, let's put a J here and a B here. And we'll put an A here and an F here. Okay? JB is a geometric mean of AB and BF. So, what that means is this. That means I can write JB is my geometric mean, so I can write that twice. And then one segment goes here, AB, and the other segment BF goes here. Now mine's not exactly like theirs, but it's very close. I have BJ and BJ, or JB and JB here. Here I have BA and BF, right here. Okay, so that's how I know that proportion is valid. Okay. Now, moving on. Notice students, it says use this proportion to find the length of BJ. So we want to find this length right here. Well, I know the length of AB. It's 1. Remember I said in the directions, these bars are 1 foot apart. Look, the total distance across from A to F is 5. So this is a foot, this is 1, this is 1, this is a foot, and this is a foot, 5 feet. So I know the distance from A to B is 1. I know the distance from B to F is 4. So it's very easy to find the measurement or the length of JB. I have JB here and JB here. For AB, I'm going to put a 1. For BF, I'm going to put a 4. So we cross multiply. JB times JB is JB squared. And then 1 times 4 is 4. Now take the square root of JB. That's JB. Take the square root of 4. And that's going to be 2. You do not need to put plus minus in front of the 2 because we're dealing with a length, okay? So it would be 2. So the length of JB is going to be 2, okay? Alright, hope that made sense. Let's go ahead and continue on and take a look at some proofs now. If two inscribed angles of a circle intercept the same arc, then the angles are congruent, okay? Alright, this should not be hopefully too difficult. I think it's about a 3-step proof, I believe. Alright, here we go. Let's go ahead and get our circle drawn here. Alright, here we go. Draw a circle. intercepting this arc here in black. So here's my arc right here. And then we'll have another inscribed angle in blue, and it'll be right here. Okay, and it intercepts the same black arc, okay? Now to speed things up, I'm going to give these angles some numbers. I'm going to call this angle here angle 1. I'm going to call this angle 2, okay? And we're dealing with arc AC. Got it? AC. So I'm going to say that I'm given okay, students, I paused the video trying to see if I could fix this pen, but I'm just not having any success, so please understand it'll be a little sloppy using the mouse, okay? But that's okay. So if, now here's what you're given, okay? So given, maybe I can, well, that's not going to work either, but here's what you're given, okay? You are given the if part, and of course the if part is 2 inscribed angles of a circle. So intercept the same arc, so we're given that. So we're given that we have angles 1 and 2 are what? Inscribed, and we have arc what? AC, okay? Then, so we're trying, there's the old pen, sorry guys. Then we're trying to prove that the angles are congruent, so angle 1's congruent to angle 2. Well guys, this is really a 3-step proof. I mean, we have our given, of course, and then look, we know from our past theorems, we can very easily state that angle 1 is half the measure of arc AC. We have a theorem that says an inscribed angle is half the size of its arc. Or, I'm not that picky, guys, or you can say the arc is twice as big as the measure of angle 1. Either way is fine, okay? And then we can also state that angle 2 is half the measure of AC, okay? So we can state that's a theorem. And then we can use substitution to set the two equal. Let me show you what I mean real quick here. Use my mouse here. Look guys, I can definitely state this, watch. I can state that angle 1 equals half the measure of what? Arc AC. And I can also state that angle 2 equals half the measure of arc AC. So substitution, I can pick this equals this, so I can pick it up and put it in for this, and I'm finished. Okay, it's really that easy. All right. So with that in mind, let's go ahead and do this quickly, and then we'll be done with this problem. So here we go. Problem number 1 is our given, of course. Put a little squiggly mark here, and we'll put given. All right. Step 2, I'm going to state angle. I'm going to put the measure of angle 1 equals half the measure of arc AC, and also in step 2 I'm going to put the measure of angle 2 equals half the measure of arc AC. And I can put them on the same step because they both have the same reason, and that's a theorem that says inscribed angle half of the arc. And that's good enough for me. If you put that on a test, I'll know exactly what you mean. And then number 3, you're done. You can state that the measure of angle 1, or angle 1, is congruent to angle 2. Substitution, and you're done. Substitution, okay. Pretty simple. Pick up this, it equals this, so pick it up and put it right there in place of this, and you're done. Alright, moving on to number 36. Now, we're going to write a plan. We're not going to prove it, we're going to write a plan. I'm going to make this pretty simple, okay? If an angle that is inscribed in this circle is a right angle, an angle that's inscribed in this circle is a right angle if and only if its corresponding arc is a semicircle, okay? So here's a picture of what we're dealing with. Here's a diameter. And this angle here in blue is an inscribed angle, okay? And it's intercepting this diameter, or this semicircle, however you want to say it, okay? So, call this circle A. Call this angle 1. Now, we have this 2 ways. We have, if an intercepted arc, if an inscribed angle is intercepting an arc, then it's 90 degrees. Or we can say if our angle is 90 degrees, then it's intercepting, let me say that again. If an inscribed angle is intercepting a semicircle or a diameter, then it's 90 degrees. Or we can say, if an inscribed angle is 90 degrees, then we know it's intercepting a diameter or an arc. Okay, so I'm going to say it this way. I'm going to say if an angle, and I did not click on Angry Birds. That's so funny, isn't it? You guys are loving this, I'm sure. That's this pen just all over the place. Well, there we go. And there we go. Yeah. Alright, for those students who are sleeping, you're awake now. Alright, I love this computer. So, moving on, I'm going to say, students, that I have a right angle here. So if, please write this down, angle 1 is a right angle, then the arc, and we'll call it arc BC, I guess is good enough for me. Arc BC is a diameter. Well, guys, my plan of attack is so very simple. I know that angle 1 is a right angle, so my plan of attack would be, I would state that, all we're doing is writing a plan of attack for this proof. I would say this, guys, you're given angle 1 is 90 degrees, so I would say the measure of angle 1 is a right angle. I would say it equals 90. Then I'd say that its intercepted arc has to be 180. This is so simple, guys. And there's a theorem we can use for that. So arc BC has to be 180. And then, by definition of a semicircle, we can state that BC is a semicircle. Because if BC is 180 degrees, there has to be a semicircle done. That's a really easy proof, guys. So we're given, if we have a 90 degree angle, then it intercepts the corresponding arc is a semicircle. So if we have a right angle, which we do, that you're given, then the angle is 90. If the angle is 90, then I know that this arc measurement is 180, because the theorem that says the measure of an inscribed angle is half the measure of its intercepted arc. And then if the arc is 180, I can say the arc is a semicircle. That's a pretty simple plan for that proof, okay? Alright, moving on to number 37. They don't want us to prove this, they want us to write a plan. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. Alright, so let's write a plan for the, let me go back, sorry. You said, Mr. Eric, what about the other way? What about saying, if I have an arc of 180, then the inscribed angle has to be 90. Guys, it's the same thing, just going backwards. If you have a semicircle, then you know it's 180, and if it's 180, then you know the angle has to be 90. So I'm not going to really worry about laying a plan out for that, okay? And some of you might be sitting there saying, Mr. Earhart, why? What do you mean by doing this two ways? Well, guys, if it's if and only if, that means you can say it one way. If I have a right angle, then I have a semicircle for an arc. The other way is, if I have a semicircle for an arc, then I have a right angle. So you have to look at it both ways and prove both ways. But the other way would be just the opposite of this, so I'm not going to take any time to do that, okay? Alright, moving on to number 37. Now, write a plan for a proof of theorem 1012. Here it is. A quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So we have two different cases here, okay? One case is this. If a quad is inscribed, then opposite angles are what? Supplementary, okay? Here's another way, then here's the other way, two different ways. If a quad's opposite angles are what? Supplementary, then it can be inscribed in a circle. Okay? So I'm just saying we have two different plans here. And I'll probably just do one like the other one we just did and just say the other one's going backwards, okay? But that's why we have two plans, alright? Alright. Now let's continue on. Let's start off, students, with this part here for no certain reason. We'll just do this one, okay? So if a quadrilateral inscribed or close enough, okay? Then the opposite angles are supplementary. So 1, 2, 3, and 4, okay? Now, let's just kind of think this through for a second, okay? Let's see. My arc from here my arcs, man, my arc from here to here, okay? Plus, we'll call this, better give them some letters, A, B, C, D. Now here's my plan of attack. I know this arc here and this arc here have to add up to 360, okay? So that's pretty obvious. So I can definitely state that arc ABC and arc ADC, if you add them up, the measure of those two arcs has to equal 360 because I'm going all the way around the circle, okay? That's pretty obvious. Now, this next part, students, will be a little difficult to understand, but stay with me, okay? So, I know this arc here, ABC, and this arc here, ADC, have to equal 360. Now, watch this, please, very carefully. That means, see this arc right here, what's the inscribed angle? Right here, there's the inscribed angle for that intercepted arc, angle 4. And what's the inscribed angle for the other arc over here? Well, that inscribed angle is the opposite angle, B. Look at that, the opposite angle. So here's what I'm trying to show you. My plan of attack would be this. Somewhere in my proof, I would say that these two arcs add together equal 360. Then I would say that angles 1 and 4, angle 1 plus angle 4 has to equal 180 because these two arcs, these two angles here make up these two arcs here, and inscribed angles have to be half of their arcs. So if the arc's 360, this has to be 180. And then, students, I would just simply change the arcs, and I would use arc BCD, arc BCD plus arc BAD right here has to equal 360. And that would say, once again, what angle made up arc BCD? Well, or what angle made that up? Angle 3. And what angle made up arc BAD right here? Well, angle 2. So then from this I would say the measure of angle 2 plus the measure of angle 3 has to equal 180 because these two angles made up these two arcs, and they have to be half of this arc. And so there we go. Then I would state that 2 and 3 are supplementary and 1 and 4 are supplementary. This one was definitely tough. I know that. I understand that. But it's still a good thinking problem, okay? So some of you probably got it, some of you didn't. And the other way would just be the opposite. I'm not going to waste time in doing that, but we just go back the opposite way and say if a quadrilateral's opposite angles are supplementary, then it can be inscribed, and you would do that by showing you have half a circle and half a circle, which is 360, and it would just be the opposite of this. Alright, number 38, we're going to prove that if ABC is an isosceles trapezoid, then ABC can be inscribed in a circle, okay? So really all we have to do is this. Go ahead and draw your isosceles trapezoid, okay? Draw that. So we know this side's congruent to this side, and we know this side's parallel to this side, and we'll call this trapezoid, like it says up here, A, B, C, D. Now, students, if we're trying to prove that this isosceles trapezoid can be inscribed in a circle, we don't really need the circle, okay, to help us. We don't care about drawing the circle like this. That's not a big deal, okay? All that we have to do is do what, students? Come on, think about it. All we have to do is prove that these two angles here, A and C, are supplementary, and prove that angles B and D are supplementary, and we should be pretty much home free. So I'm not going to give these angles numbers, because we have letters for each number. Angle A, angle B, angle C, and angle D. So, first of all, I'm just kind of brainstorming. I'm just going to try to do a plan of attack. I know I can state that A is congruent to D, because we're told that base angles of a isosceles trapezoid are congruent. Thus, that also means angles B and C are congruent because they're also base angles. Remember, base angles are just the angles on the end of the parallel sides. Now, I also know this, guys. Look, I have two parallel sides cut by a transversal right here, consecutive interior. So I know angles A and B. And also, look, here's my transversal over here, consecutive interior. So I know A and B are supplementary, and C and D are supplementary. So I know somewhere in my proof I can state that A plus B equals 180. And somewhere in my proof I can state that C plus D equals 180. Alright, and now I want B and D to be together. So do you see how B is congruent to C? What can I put for C right here? B. So for C I can now put B. B plus D equals 180. Booyah, that's what I wanted. And look at this, I want to have A and C together. I want to somewhere have A and C equal 180. I have A and B right here, okay? But, let's see, did I make a mistake here? Hold on one second. A is congruent to A and B are supplementary, C and D. B is congruent to C, A is congruent to D. Okay, students, I'm back. Sorry. Yeah, so I want A and C to be supplementary. Well, B is congruent to C, correct? I don't even need this, so cross that off. And when you're brainstorming, guys, I'm not embarrassed of that because when you're brainstorming, you're supposed to list out everything you can think of and then use what you need. So B is congruent to C. So for B right here, I can put C. So I have A plus C equals 180. So there we go. I'm looking pretty good. I'm going to take this right here and drag this out of the way to give me more space. And this drawing here is so perfect and beautiful. I don't want to delete that, so we'll put it up here. And this is all of our information here that we're going to use during our proof. Okay, we'll look up at that and we'll use that. So, here's what I'm given. Let's go ahead and write our given right here. If I can get my pen to work, you're given that you have an isosceles A, B, C, D is an isosceles trap. And you're going to prove that it can be inscribed. Alright? So here we go. You got your step one. That's your given. I'm not going for neatness here, I'm going for speed, guys, okay? Next, I can state that angle B is congruent to angle C because we know that base angles of an isosceles, base angles congruent. We know we have an isosceles. Also, we need to state that BC is parallel to AD. And we can do that by definition of an isosceles trap. So definition of isosceles trapezoid. Okay? Alright, now, next we can state that angles, let's see, angles A and B, angles A and B are supplementary, and angles C and D are supplementary. Okay, and that's why. How can we state that? Because consecutive interior angles are supplementary. Okay, now if I state they're supplementary, then next I'm going to state they equal 180. So angle A plus angle B equals 180, and angle C plus angle D equals 180. Alright, and of course that's definition of supplementary angles. Now I'm going to come up here and do some erasing if I can get my mouse to work. I better not do that. Okay, we're going to need that information. Alright. We'll just try to squeeze it in, the rest of it in right up here in this little area right here. If at all possible, right up in here. Alright, so here we go. Now, actually I'm just about done anyways. So, if B is congruent to C, for B right here, I can put a C. So now for step 6, I have A plus angle A plus angle C equals 180. Alright, and I can also put B in for C right here. Right here, see I can put B. So I have angle B plus angle D equals 180. And the reason would be, folks, substitution. That's substitution. Alright? Now, moving on to number 7. Because I've stated they're equal to 180, I can now say that the quadrilateral ABCD can be inscribed. Because the reason is opposite angles are supplementary. Opposite angles supplementary. Now, I did leave out one small step because I ran out of room. Really, if you listen to me, students, on a test request, I probably wouldn't be that picky, but I want you to know that really step 7 should have been after you state that A and C equal 180 and B and D equal 180. Then for step 7, I really should have said angles A and C are supplementary, angles B and D are supplementary, and the reason would be definition of supplementary angles. And then step 8 would have been the quadrilateral ABC can be inscribed because the opposite angles are supplementary. But I really ran out of room here, and on a test or a quiz, I wouldn't have taken off for that anyway, so it's totally fine. Okay, so there we go. Let's move on now to some more problems, okay? Numbers 39 through 42. 39 through 42, here we go. The quadrilateral is inscribed in a circle. Solve for x. Okay, so here we go. We're going to solve for x. Well, students, let me get a picture up here once and for all for you, okay? You have quadrilateral EFGH. So I'm going to draw any quadrilateral I feel like. And I'm going to put EFGH. We're going to use this same picture over and over for the next 4 problems, okay? There we go. Now, let's copy this and do that. Alright, and here we go. Now, students, the reason it's very important for you to see this picture is to know they're telling you this quadrilateral is inscribed. Now, if it's inscribed, that means E and G add up to 180 and H and F add up to 180. So, notice they give me E and G. So, if I take E, which is 9x plus 7, right? Plus G, which is 5 parentheses 21 minus x, that should equal 180, correct? Because I'm taking this angle here plus this angle here. So let's see what I get. 9x plus 63 equals 105, not equals, plus 105, 5 times 21, minus 5x equals 180. Now simplify your left side. 9 minus 5 is 4x. 63 plus 100, 5 is 168. Now get x by itself, so bring the 168 over, make it a negative 168. 4x equals 12. So x equals 3. Now the direction said to solve for x, and then find the measure of h. So, you said, Mr. Aaron, we can't find the measure of h. H isn't up here. True. But if I can find the measure of f, then I can find the measure of h, because these two angles are supplementary. So, here's angle F right here. 6x plus 12. You see that? Angle F. So where the x is, I'll put a 3. 3 plus 12 is 15. 15 times 6 is 90. 3 plus 12 is 15. 15 times 6 is 90. So if this angle is 90, h and f are supplementary, then this has to be 90 also, because 90 plus 90 is 180. So 3 was x, 90 is angle h. Let's try another one, okay? Here it is. Now, okay, we have, once again, E and G are across. So E is x squared plus 20 plus G, which is 2, parentheses, x squared minus 40, and all that should equal what? 180. Now let's simplify. So next we would have x squared plus 20 plus 2x squared minus 80 equals 180. Now combine your like terms. X squared plus 2 is 3x squared. 20 minus 80 is negative 60. Bring the 60 over and make it a positive 60. And now you're left with 3x squared equals 240. Divide both sides by 3x squared equals 80. Take the square root of both sides, and you should get, well, they're putting 4 square root of 5, which is fine. Take the square root of both sides, and x equals the square root of 80. Alright, but don't forget we're going to break that down into perfect squares if we can. 16 is a perfect square. 16 times 5 is 80. So 80 is 16 times 5. Cross off the 16, put a 4 on the outside. We've learned how to do this. So x equals 4 square root of 5. So there's x, okay? 4 square root of 5. Now, they want us to find the measurement of angle H. So first we got to find the measurement of angle F, okay? So angle F is 4 parentheses. See the x right here? See that x? I'm going to go ahead and put 4 square root of 5 plus 5. Now I wonder if they want this in a decimal. I think they would. So with my calculator, I'm going to take 4 times the square root of 5 right here. 4 times the square root of 5. And I'm going to get 8.944 and then plus 5. And then multiply that by 4. And if you do all that correctly, you're going to get 55.7. I'm going to put 56 for this angle. So if this is 56, then this has to be 34 over here. Because that's not correct, I apologize. This would have to be 61 at 124 degrees. Because these two angles here have to add up to 180. And they're going to have a decimal in their answers. I just rounded mine to whole numbers. Okay, let's continue on. Let's try some more of these. Alright, okay, here we go. Now, there's the quadrilateral we're going to look at. E and G are across from each other. So I know if I take E, x squared plus 15, plus G, which is 6x squared minus 10, add them together, it should equal 180. Alright, so add your like terms, 7x squared, add your like terms, positive 5, 15 minus 10. So there I completely simplified the left side, okay? Now I'm going to get x by itself, bring the 5 over and make it negative. So 7x squared equals 175, okay? Now divide both sides by 7 and you're going to get 25. So I have x squared equals 25. Take the square root of both sides. X equals 5. Alright? So, x equals 5. Now, we're going to go ahead and put 5 in for x right here. Okay, right there. So, 27 times 5 would be 135. So that's angle F. Now, if angle F is 135, then this angle over here has to be 45 degrees, because 135 plus 45 gives you 180. Alright, so 45 degrees is angle H. Last one, done the exact same way once again. We have E and G across from each other, and so angle E is 17x squared plus 22. G is 23x squared minus 2 equals 180. Alright, add your like terms and you'll get 40x squared. And we have, let's see, 22 minus 2 would be positive 20 equals 180. Now bring the 20 over, make it negative, so we can get x by itself. 40x squared equals 160. Alright, then take 160 and divide by 40 and you'll get 4. So x squared equals 4. Take the square root of both sides. X equals 2. So we know x equals 2. Alright, now for angle F, we're going to put a 2 in for x right here. So I have the square root of 50, whatever that is, times 2, and then minus 5. So grab my calculators. Square root of 50 times 2 minus 5, and I'm getting 9.14. So I'm going to put 9 degrees. Alright, so if that's 9 degrees, then this has to be 171 degrees over here to give you supplementary angles. And then you get 170.9. I have 171. Definitely close enough, okay? Alright, moving on now to numbers 43 through 46. Solve for x. The given figure is a semicircle. Well, students, I would like to show you first of all that you have congruent sides here of a triangle. So if you have congruent sides, then you definitely have this angle here being congruent to this angle here. Alright? Also, if this length here is congruent to this length here, which it is, if two chords, listen to me, if two chords are congruent, then their arcs are congruent. So this arc here has to be congruent to this arc here, and we know we have a semicircle, so the whole arc's 180, so this arc has to be 90 degrees. This arc has to be 90 degrees. So the inscribed angle for 90 degrees is this right here. There's the inscribed angle right there. That inscribed angle right there intercepts that arc. So if that arc's 90, that means this angle over here has to be 45 degrees. So I'm going to go ahead and put 45 degrees here and 45 degrees here. Why does that matter? I want to show you that you have a 45. Well, if this is 45 and this is 90, this has to be 45 up here. This has to be 45. Guys, you have a 45, 45, 90 triangle. Here it is. 45, 45, 90 triangle right there. And what do we know about 45, 45, 90 triangles? Their legs are congruent. So if this is 4, this would also have to be 4 here too. Alright? So 4 and 4. Okay? Alright. Moving on to number 44. Now, notice what you have here, students. We have an inscribed triangle here. Okay? And I notice I have a right triangle with an altitude being drawn to the hypotenuse. That means this number here, 6, is the geometric mean of this and this. Okay? We just had a test over this. So this length here is the geometric mean of this segment here and this segment here. So you always write your geometric mean twice. Always diagonal from each other, and the other two numbers go diagonal from each other. So there we go. 2 times 2 square root of 3 times x is 2. Square root of 3x. 6 times 6 is 36. Now, divide both sides by 2 square root of 3. So x equals 36 over 2 square root of 3. Now this is an outside number, and this is an outside number. In other words, they're not under the radical. You could not simplify or reduce the 3 and the 36 because 3 is under a radical and 36 is not. But you can simplify these two numbers here. 2 goes into both of them. So you're left with 18 over the square root of 3. Alright? We'll rationalize your denominator. Multiply the top and the bottom by the square root of 3. We know how to do that. And you get 18 square root of 3 over square root of 3 times square root of 3 is 3. And you think you're done. And you are pretty much. But look, 18 and 3 can be reduced. So 3 goes into 18 6 times. So your final answer is 6 square root of 3. Okay? A lot of steps there, but not too difficult of a problem if you know your geometric means, okay? This segment here is the geometric mean of these two segments here. Alright, number 45. A similar problem, guys. A somewhat similar problem. We have a right triangle again with an altitude drawn from the right angle to the hypotenuse, okay? So pretty similar problem. I know this number right here is going to be my geometric mean of this segment here and this segment here, okay? So if I'm going to find x here, probably the easiest way to do this would be to let, if this entire segment is 25 and this much here is x, then I would say the segment from here to here would be 25 minus x. That should make sense. Let's pretend x was 12, okay? And this whole thing's 25. How would you find this length here? You would take the whole length, 25, minus 12, and this length here would be 13. You would take 25 minus 12. Well, the 12 is not 12, the 12 is an x. So it's okay. We're just going to say if this is x, then the whole length, 25, minus x, gives you this segment here. So 12 is the geometric mean of this segment here and this segment here. So you write your 12 twice. And then one part would be 25, and the other part, no, one part would be x, excuse me, and the other part would be 25 minus x. Now, go ahead and cross multiply. 12 times 12 is 144. And x times 25 minus x would be 25x minus x squared, okay? Now, I'm going to move everything over here. I'm going to move everything to the left side. So my x squared gets moved over. left side, okay? So here we go. Bring your negative x squared over, and it becomes a positive x squared. Bring your 25x over, becomes a negative 25x. So this got moved over, became positive. This got moved over, became negative. 144 stays where it is. Now, if you'll notice this year in geometry, because we have a lot of Algebra 1 students, I've not put, I don't think, any factoring at all on tests or quizzes. Although I probably should, but I haven't. It is a Track 1 class, so I probably should. But anyways, just in case you struggle with factoring, you would have to factor this now. So I would say to myself, what two numbers when multiplied together would give me 144, but when add together would give me negative 25. And there's a lot of different numbers, okay, for 144, but the two numbers end up being negative 9 and negative 16. If you multiply those two numbers, you'll get a positive 144. If you combine them, you get a negative 25. So the factorization would look like this: x minus 9, x minus 16 equals 0. And then what you do is you take each group and you set each group equal to 0. Bring your 9 over and make it positive. Bring your 16 over and make it positive. So there's actually two possible answers for letter x. X could be 9. And think about it, guys. Let's get all of this cleared out here and just think about something for a second, okay? Watch this. Now watch this carefully. One answer for x is 9. So if x was 9 right here, then this segment over here would have to be 16, because 9 plus 16 is 25. However, if you said x was 16, then this segment over here would have to be 9, because 9 plus 16 is 25. So either way, either x is 16 or x is 9, okay? Either one is fine. Okay, long assignment today. Last but not least, let's take a look at number 46. Alright, well guys, I mean, this is just like the first one we did way back before. I mean, once again, look, we have this segment here. Well, I can't get this thing to work. Okay, there we go. It's almost like the very first problem we did in this section, number 43. We know this segment here is congruent to this segment here. Okay, we know that. And so, obviously, once again, we're going to have, well, in this case, we're going to have congruent triangles because they share a side too. And they're both right angles, so we have side angle side of one triangle being congruent to side angle side of another triangle. So these two triangles are totally congruent. So we'll call this triangle 1 and triangle 2. They're totally congruent. If they're congruent, then all their parts are congruent. If all their parts are congruent, then this segment here is congruent to this segment here. Now, if this segment here is congruent to this segment here, that means this chord here is congruent to this chord here. We've learned whenever two chords are congruent, their corresponding arcs are congruent. So this arc here is congruent to this arc here. Now, if that's the case, we know we have a semicircle because it says that in the instructions. So this whole arc is 180. So if the whole arc is 180, then we know these two arcs have to be 90 each. So this arc here is 90. This arc here is 90. What's the inscribed angle? Well, the arc goes from that black dot there to this black dot here. So the inscribed angle is here and here, and that means this inscribed angle right here is half a 90, 45 degrees. Okay, so I did all of that to show you what we really have is a 45. Once again, we have 45, 45, 90 triangles. Okay, that's all I wanted to show you. So 45, 45, if I can get this pen to work, 45, 90. So we know if this whole thing's 10 and this much, and the two segments are congruent, this segment here is congruent to this segment here, then that tells us that this segment here is 5 and this segment here is 5. So legs in a 45, 45, 90 triangle, the legs are congruent. So if this leg is 5, then this leg here is also 5. There we go. Okay, pretty long assignment, but it's been good problems, good practice for you guys. If you have any questions, I hope this homework help video has been help to you. If you have any questions, don't hesitate to